Hi, welcome to the Advanced Math, Unit 11, Trigonometric Identities and Formulas, Part E, classwork, walkthrough. As usual, before you watch this video, you should try to do this on your own and check your work against the answer key. If you're stuck on something or something you think could use a little more explanation, then watch the video. So we've looked at angle sum and angle difference formulas for sine, cosine, and tangent so far. So that's the situation. Sine of a plus b. A and b are different. And we've worked out a formula for that before, and now we're saying, well, what if they're the same? Sine of a plus a. And that's really sine of 2a. So we want to look at what these formulas for angle sum and difference, or really just angle sum, look like when we're using the same angle for both of them. And that whole sort of category of formulas are called double angle formulas. So we're going to look first at the double angle formula for sine. So remember, the formula for sine of a plus b is sine, cosine, cosine, sine. So we'll write that out, filling in the a's for both the a and the b. We'll see what I mean. So sine, cosine, and this is a plus, so we're going to use a plus. Sine, cosine, cosine, sine. And I just wrote out the names of the functions because I'm trying to remember in my own mind how this goes. Sine angle sum formula is sine, cosine, cosine, sine. And so I have to remember that. And then I'm going to poke in the arguments. So the first argument goes here, second argument goes here, first argument goes here, second argument goes there. And they're all a's, so it's really easy. So this becomes sine a, cosine a, cosine a, sine a. Okay, yeah, this isn't rocket science. So it's sine of a, cosine of a, plus cosine of a, sine of a. Stop and think for a moment. Sine of a, cosine of a. This is sine of a times cosine of a. This is cosine of a times sine of a. These are the same thing. The order in which we're multiplying the sine and cosine is different, but in multiplication, the order in which you write the multiplication expression doesn't matter. So in fact, these are two of the same thing. So I can simplify this and say that sine of 2a is really 2 times sine of a times cosine of a. Or, since we're doing multiplication, only the parentheses don't matter, 2 sine of a cosine of a. And you could write that as 2 cosine of a sine of a. It doesn't really matter. The norm or convention is to write it as 2 sine of a cosine of a. So that was easy. Let's try doing it for cosine. So cosine angle sum formula is cosine, cosine, sine, 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 where the extra sign is used to show you that, or remind you that, the sign of this operation is opposite what it's shown here. So cosine, cosine, sine. There's the negative where we had a positive shown here, where you want to use a negative here. That's what you used for the cosine function. It's the oppositeness. Cosine, cosine, sine, sine, sine. And I'll poke in the arguments. This is cosine of a, cosine of a, minus sine of a, sine of a. Okay? Now, we have to think a little bit. This isn't going to simplify as nicely or as easily as the last example. Cosine of a is not the same as sine of a, sine of a. It's not that closely related. However, we could say that that is cosine squared of a minus sine, minus sine squared of a. And you might remember from some work we've done earlier that whenever you have cosine squared or sine squared, you should be thinking about using the Pythagorean identity to rewrite it. So let me crank that one through. So we've got this one version, which I just wrote. I'll write it again. Cosine of 2a certainly is equal to cosine squared of a minus sine squared of a. And you know, when you're looking at some expressions you're trying to simplify, and if you ever saw this as an expression, your first thought should be Pythagorean identity. But remember, the Pythagorean identity says that cosine squared of a plus sine squared of a equals 1. Cosine squared of a minus sine squared of a is not equal to 1. It's equal to something else. So if you did see this in an expression you're trying to simplify, what you could play around with is substituting this and say, well, it's really the same as cosine of 2a. Does that help me any? It may or may not help you, but that's just something to try to remember. When you see cosine squared or sine squared, just remember that there is probably something you can do with it. And if it's cosine squared a minus sine squared a, that thing that you can do with it is converted to cosine of 2a. All right. So let's try finding a substitution for sine squared of a using the Pythagorean identity. So one way of writing the Pythagorean identity would be to say that sine squared of a equals 1 minus cosine squared of a. So that's a rewriting of the Pythagorean identity. And you could try, if you're unsure, you could say, well, if I added cosine squared of a to both sides, I'd have sine squared of a plus cosine squared of a equals 1. And that's the Pythagorean identity. So this is just a rearrangement of that, and it's equivalent essentially to the Pythagorean identity. So that means the sine squared a I have here, I could substitute with this. And that leads to cosine of 2a equals cosine squared a minus 1 plus cosine squared of a. And you might be wondering where that plus came with. So this is a minus this whole thing. So we're applying the negative to this, and we're applying the negative to this. So this became a negative 1, and this became a minus negative cosine squared of a, which of course would be a plus cosine squared of a. And then we have 2 of these cosine squared of a's, so we could say that this is in fact 2 cosine squared of a minus 1. So that's, if this is one way to write the double angle formula for cosine, this is another way to write the double angle formula for cosine. So if, for example, you had a situation that you're trying to simplify some trigonometry and you see this 2 cosine squared of a, you could think about, I wonder if I can sort of finagle that into a cosine of 2a plus 1 or something like that. So this becomes, this cosine of 2a equals 2 cosine squared of a minus 1 is an identity. I'm going to write it down again here just to nail it. Okay, so that's one thing we could say. So just as I rewrote the Pythagorean identity up there, I can rewrite it again in a similar way, solving for cosine squared. It's because cosine squared of a equals 1 minus sine squared of a. And that leads me to yet another version of this double angle formula for cosine. So cosine of 2a equals 1 minus sine squared of a minus sine squared of a. I am taking this and substituting it for this. So this shows up here, and then this just comes down from above. So we're starting with this as a basis and making a substitution for the cosine squared of a, and we get something that's entirely involving sines. And that's kind of nice. So the punchline. So we have this version, we've got this version, and we have this version. So those are 3 variations, all really equivalent to each other, thanks to the Pythagorean identity, that are essentially the double angle formula for cosine. Okay, so those are 2 biggies. The last one is saying, hey, let's do this the same thing with tangent. And I got to tell you, the tangent one, frankly, doesn't thrill me that much, but we're going to put it in here just for completeness sake. Tan of a plus, and all I'm doing is writing, this is the angle sum formula for tangent, no biggie. And remember, the angle sum formula for tangent, it's got plus or minus showing up here, and a minus or plus showing up here. So the sign here, plus, has to be opposite the sign here. The sign here has to match this, and this one's got to be the opposite. And the rest of the denominator was tan of A plus times tan of B, so this becomes tangent squared of A, because we're multiplying tangent of A times tangent of A. So lastly, with just a little bit of simplification left that I can do, I have the tangent of 2A equals 2 tangent of A over 1 minus tan squared of A. So this tan A plus tan A becomes 2 tan of A. And so that becomes the double angle formula for tangent. Now, this is the end of the page, but I just want to talk about one last thing. If you've been paying attention, you might think to yourself, here I've got cosine, for example, cosine of 2a. So cosine of 2a, I've got a variable here, and it's multiplied by 2 inside the parentheses. So thinking back to function transformations, that means that the graph of this should be compressed horizontally by a factor of 2. And that changes the period of the cosine function. And if I go over here and look at what's going into the sine, I'm taking sine squared of A. A doesn't have a 2 in front of it. It seems like it should have a period that's the original period, 360 degrees, or 2 pi. And yet this period's going to be compressed horizontally. It should have a period of 180 degrees, or just pi. How do we get this compressed graph from the square of sine of A? That seems really strange. Okay, so I just want to talk about that for a moment. So I'm going to sketch a graph of the sine of A. Just one cycle of sine of A. And I want to think about what happens when you square that. So the parts of the sine function that are positive are going to remain positive. And the parts that are negative, when they get squared, they're going to become positive. And let's think about what that's going to look like. I'm going to change my color here a little bit. So when the sine function, is 0, the square of 0 is going to be 0. When the sine function is positive 1, the square of 1 is going to be positive 1. When the sine function crosses back into the negative land again, that's 0. The square of 0 is 0. And when the sine function is at negative 1, the square of negative 1 is positive 1 again. And then at 0, it's 0. So what you get here, actually, ends up looking like this. Oh wait, let me expand this a little bit. Ends up looking like this. So, and remember that our double angle formula is multiplying that by 2, which gives it a vertical stretch, and subtracting it from 1, which flips it upside down. So in the end, what you end up with is a graph that has the same amplitude as the first one, and has 1/2 the period of it, and is in fact a cosine function, which starts up here. So, there we go. Remember, we are doing here the cosine of 2a, so we're expecting this red curve to be a cosine, and it is. And because it's 2a, we're expecting the period to be 1/2 what it normally is, compressed horizontally. And it is, because this was generated from the blue curve, flipping it upside down and multiplying it by 2. So that's why this actually makes sense.